So today we are going to learn our second machine learning model, specifically classification model. And we call it naive Bayes classification or naive Bayes algorithm. Now, if we remove the word naive, then it's essentially the Bayes theorem. And the Bayes theorem is something that you should already know. But we will go over briefly what Bayes theorem was, how it can help us to do classification. But then we will mainly focus on the naive part and why that is important in this machine learning class, okay? Before we start, any questions on anything? Yes?
So the previous assignment, it's regarding the data set. Like, I've tried to solve it, but I've been getting the gain information values in negatives. It's like 0.000, and it's a negative part. So is it correct the way I'm going, because getting that many zeros at the point and going
Let's talk about the assignment details in my office hour, okay? After this class. It's a very specific question. So if you have something general. All right. Oh, okay. Yeah.
How long does it take for the assignments to typically be graded?
It should be graded within a week of submission. So you should expect your grades to be available for your assignments after the deadline, like within 1 week. If you don't see it, let me know. I'll poke the TAs to make it faster. Okay? All right. Yes?
So from here going forward, it looks like most of the assignments you're going to be due on Tuesday. Are all of those going to be opened up after the previous class is Tuesday? Like the naive one will be open after today's class?
It depends on how the lecture goes. I'll try to publish this. I think most likely the next assignment will be published today. But because it is on naive Bayes, we didn't submit or publish the assignment earlier because we haven't taught you the topic yet. So the next assignment will be on naive Bayes. So that's why we are going to publish it today. All right? Okay. So before we talk about Bayes theorem and everything, so this is coming from the probability theory, right? So all we are talking about here is a probabilistic approach to learning. And when we talk about Bayesian probabilities, we are talking about evidence, we are talking about hypothesis, and we are talking about priors. So it's very important to understand what those terms actually mean, right? So the whole idea is, instead of learning the function itself that can transform x into y, you want to know what is the probability that I will see a particular y given x. That's the probabilistic approach to learning, right? I'm not going to learn the function itself that maps x to y. Rather, I have a predefined set of values for y. I just want to know how likely those values are going to be based on which value is mostly likely based on the value of x that we see. So what does that mean? Let's start with the classic Bayes rule, right? How many of you remember this? How many of you have no idea what is this? Okay, everybody has got some idea. How many of you are still auditing? 1, 2. That's it? Okay. So, probability of A given B is equal to probability of B given A, probability of A divided by probability of B. This is the Bayes theorem, right? Now, what does this really mean? Let's say, first of all, let's take this one on this side, right? what does this mean, the left hand side?
Saying the probability that B happens and the probability that A happens given B.
Okay. So can we say this essentially means that probability that A and B both happens together,
Yep.
right? How about this part?
Probability of B given that A occurs
Yes, times.
times for probability of A.
Is that the same thing?
Yeah.
Yeah, so that's why they are equal, right? That's why Bayes' theorem is coming from. So now it just uses a different representation for the joint probability. It just reorganizes terms. But it helps us figure out this conditional probability in terms of other conditional and prior probabilities. Now, tell me from this equation which probabilities are conditional probabilities and which probabilities are prior probabilities.
P of A by B and P of B by A are conditional.
So this one is what? Conditional. Okay. This one?
Conditional.
Condition. Okay. This one?
Prior.
It's a prior, right? It doesn't depend on anything. What about this?
Prior.
It's a prior. It doesn't depend on anything, okay? Okay. Now let me replace A and B with something that we use for machine learning, okay? So let's say A is a random variable that represents our class. The hypotheses are basically different classes. And B is essentially our data. Right? Now, how does this change our notion of Bayes in case of machine learning? So we have probability of a class given data, right? And then we basically say probability of data given class, probability of class, probability of data. I just replaced A with a class and B with data. This is the same Bayes theorem, right? Now, what is a classification task? You have already done in your assignment of decision tree, right? You have an instance, an example, a training example, right? Or a testing example, that's your data. And based on that, you want to find which class this example belongs to, this point, right? But now, as I said, now with a probabilistic like interpretation or view, instead of saying directly inferring like this data should map to this class, we want to find out how likely this class is given that we see this data. So we are formulating everything in terms of probability. We want to compute a probability number. Given this data, what is the value that this class random variable should take? What is the probability? So we are thinking formulating the problem in terms of a probability distribution. So the first question is, do we know this? Let's say you are just initially given a data set, right? A training data set. And based on the data set, we need to figure out whether we know this or not. Right? Yes?
Yeah, can't you go through and find out every instance in which the data is true and line that up against every instance that's true? Don't you just know that and start?
Right. So let's say I give you some data and I give you some labels. So this is X, this is Y, right? So if I know that for some particular data you have a particular Y, then I could, let's say if I have data number 1, data number 2, data number 3, and so on, right? For each data point, you will see some labels. Now, each data point is unique. And you may also see conflicting examples where there are two different x1 and x2, they map to different y's. But the point is, if you want to estimate this probability directly, what is a big problem with this? If I try to estimate this probability from this data set, what is a big problem?
There could be other attributes that indicate that class, maybe, like how do you definitely delineate what defines that class, I guess?
Think about in terms of number of class versus number of data points. Yes?
Data might just be a sample.
Yeah. And then so the point is, you could have millions of data points. And you could have only few classes. Then for each data point, you need to learn a single model. Probability, right? You need to learn a lot of probabilities, but then these are just single points. To estimate a probability, you need a lot of data, but here, that's not just a convenient way to compute probabilities for each data point that may be very unique. It's against the point of generalization in machine learning. That's where Bayes' theorem comes into play, because this is hard to estimate, right? And you will never have all the possible data in your training data set. You will miss a lot of examples there, or a lot of cases. So let's flip the problem using Bayes' theorem, and let's come to this. Because for each class, you will see a lot of data, because you have flipped the problem. Now it's not about for each data you want to find a class, which we actually want to do, but to estimate these probabilities. Now we have flipped the problem because we have many, many examples for each class mapping to some data. Think about a dog class for which you have a lot of pictures. But for one picture, you could only have one label most of the time if it is not a multi-class classification problem. So the estimation of probability also doesn't make sense there. And then you will also have a lot of images of dogs versus cats. So you can define a prior probability as well. But there is still this problem. Which one? Which one is the problematic part? This guy. Think about the entire space of data points. Then one particular point in that space, what will be the probability of this? Almost close to 0, right? I mean, this is the basic problem, why we initially flipped. because this is just mostly like one point, and computing a probability for a point doesn't make sense. But again, we have to compute it here. But the good thing is, we actually don't need to compute this. Why? Why we don't really need to compute this? So think about this. Yes?
Is it possibly because each individual data should have the same probability or something?
Exactly. So think about this. You have two classes, right? Given this image, you want to classify whether it's a cat or a dog. Given this image, is this image changing? No. It is fixed. The probability of that image is fixed. Whether it's a dog or a cat, the label, the probability changes. So the point is, the probability of this image is actually constant for this classification task. The image is given. It's given. Your data point is given. All you are trying to do is to find out what is the class. So what you need to do is, you need to compute what is the probability of class 1 given the data, and what is the probability of class 2 given data. And you just need to compare these two. You don't need the actual values. You just need to find out which one is higher. But both of them has got this guy as a denominator. So you basically don't need to compute this number in order to find out which one is higher. So now we have solved this problem using Bayes' theorem, that you can compute the probability of a hypothesis to be true or the class to be true by flipping the problem in terms of two different probabilities and computing them. And then if you compare against different classes, you will see which one is the most likely. So this term is called the prior. We already talked about this. This part is called the likelihood. And this probability is called the posterior. So what Bayesian classification does is estimate likelihood and prior, and based on the likelihood and prior, try to infer the posterior. Questions so far? Yes.
Repeat what you just said.
Bayesian classification algorithms try to learn the likelihood function and the prior probabilities, and based on that, it tries to infer what is going to be the posterior probabilities. And based on the maximum posterior, it makes a choice, like which class to assign. Okay? So it's important to remember these two terms, posterior and likelihood. Likelihood is, given the class, what is the probability of the data? This is the evidence part. How likely is your evidence? Likelihood. And the posterior is basically, given your data, what is the likelihood of the class? So how likely your hypothesis is, not the data. Okay? All right.
So
Yes.
Did you get rid of the denominator? And you said it's because it's like a constant?
Yes.
Okay.
It's constant for a particular data point, because you are classifying one particular image, right? Or a particular document, a particular sample that is given. All you need to know whether it belongs to a particular class 1, class 2, or class 3. The data is constant. Okay. So there are two possibilities, right? actually three possibilities that x is actually 4, right? X and y. X could be discrete or continuous, and y could be also discrete and continuous, right? For a classification task, can y be continuous?
No,
Why not?
to define, you have to delineate the classes, right?
Yes. So it's by definition. Class has to be a fixed set of items, right? Labels. It has to be discrete. That is the definition of class. If y is not discrete, it's continuous, then it's not a classification problem. It becomes a regression problem, right? It's a continuous variable you are trying to estimate. So because right now we are talking about classification, so y cannot be continuous. So that part is gone. Y is always discrete because that's how classification problems are defined, right? So we have two possibilities. The x could be discrete or x could be continuous because y is always discrete. There is no change, right? So let's consider the case where x is discrete for now, and we'll go to continuous case. And remember, in case of decision tree, when we learned how decision tree works, what was the assumption we made on x? Was x continuous or discrete?
Discrete.
Discrete, right? And then how did we handle continuous cases? We bind them into discrete labels, right? Okay, so again, here the good thing about Naive-Bayes is you don't have to bin. There are like options to deal with. There are ways to deal with continuous data directly, but we will first see the discrete labels first, okay? Okay, so x has a fixed set of labels, and let's say we want to find out, we are given a data point which is a new data point. This is an unseen data, which is a tuple, has got attributes x1, x2 till xn, right? Now we need to figure out which class is most likely, which label is most likely for this particular instance. So we need to figure out what is the most likely y, right? And y could have, let's say, k different values given this x new. This is what we need to figure out. So we need to figure out for all values of y, k different values, what are the probabilities? And then find out which one is highest. That one is the most likely label for this example, for this data point. And if we apply Bayes' theorem, it's basically we flip the problem, right? We flip the problem. We say x new given y, probability of y divided by probability of x new. But then we actually showed that we don't need to compute this because this is constant. We get rid of this. So this is proportional to this.
So is x new not a single data point then?
It's a single data point, yes. It is a single data point. You are trying to figure out, given this data point, what label it should take, which is proportional to if y is the actual label, and this is should be equal to this, right? How likely this class actually generates a data point like this times how likely is the prior probability that this class happens, right? Now, it's all about flipping the problem in Bayes, right? You want to figure out the label, but this probability is unrealistic to compute. So you flip the problem, which are into two different probabilities that are realistic to practical to compute based on some training data. One is the likelihood and the other one is the prior. Now the whole point is, how do you figure out these two probabilities? Right? Okay. But still we have a problem, right? For example, this one seems, which one seems harder to compute? Which of these two?
X new.
Probability of, this term is harder?
I guess because it has X new in it, yeah.
Okay. But tell me why. It has X new, it has more terms for sure. But what is the exact problem?
Defining X new? I'm not sure how you get X new from X1, X2 to Xn.
These are just features. Think about your decision tree, those columns,
And those that you combine into,
like the weather,
right.
humidity, these are X1, X2, X3. These are features, attributes.
That you use to define your single data point X new.
Yes, so these are attributes that define a data point. Those rows in the table that you have seen in the decision tree example.
And your Y, do you know, are those labeled or do you know?
Yeah, this is play tennis. Yes or no.
So you already know the answer. Or,
If it is a training data point, you know.
right.
If for a testing data point, you don't know.
So isn't that just counting? That's why Y seems simpler to me.
This one seems just counting. Why is not this one also counting?
I guess you just have to count a little more.
You just have to count more. Exactly. Yes.
Right.
Yeah.
The one on the left is a subset of the subset. So yeah, it's just a different type of counting. The denominator is different.
Right. So the point is, you have, when we compute probabilities, we essentially count things, right? And then we do some sort of ratios. Now here, for the prior probability, you just need to look at what are the possible values of y. Think about play tennis. Yes, no. Just two possibilities. You just compute these two probabilities. Actually, you compute one. Why?
No,
The other one is
1 minus the
1 minus that, because that's the distribution. But here, you compute many, because for play tennis equals to yes, you have to compute weather equals to this, humidity equals to this, and all the values possible. And then again, for play tennis equals to no, you have to again compute weather equals to this, humidity equals to this, and so on. So many possibilities, right? That's the problem. We have flipped this problem that is practical, but is it really? Let's try to think about something. Let's say we want to classify people. Any people, any person in the world. Okay? Based on 100 features. We have 100 features like height, width, race, let's say. And the label could be anything. We don't care. But let's say we want to classify people with 100 features. Your age, income, like this, so on. So if you have 100 features, and let's assume that they are binary features, how many combinations you can have for those data points, for those features?
2 to the 100.
2 to the power 100, right? So if you have a 100-dimensional vector to represent, so x1 could be binary, 1, 0. x2 could be 1 or 0. Let's put second bracket. x100 could also be 0 or 1. then you could create 2 to the power 100 different x. Which is equal to 10 to the power 30 or something. Close to. How many people we have in this world today?
8 billion?
Sorry?
It's like 8 billion now?
Let's say, let's do 9 billion or whatever. I think that number will be something like this. So, for how many features you will not even find a person to map to?
Almost all of them.
Yeah. So, here is the problem. Sorry, not that. This one. So, number of people on earth is 10 to the power 9, and then you need to estimate 10 to the power 30. So, fraction of rows with 0 training examples will be almost 1. Still a big problem. So Bayes, very cool theorem, very intuitive, makes a lot of sense, gives us a way to compute probability that actually looks sensible, still we cannot do anything with it. Right? That's where the naive part comes into play. And although that is naive, that works. Okay? So, what we do? We make an assumption. We make a simple assumption, which is a dumb assumption, which is a silly assumption, but we make it because we have no other way. The assumption is all these x are independent of each other. They don't influence each other. Why is that helpful? Let's think about again number of computation we need to do. So initially we said if we have n attributes, right, we need 2 to the power n probabilities to be estimated, right? Actually 2 to the power n minus 1. Why? Why? Why minus 1 is enough?
You can't calculate the last probability, but by 1 minus.
Yeah, because it sums to 1. Because probability distribution sums to 1. You are getting all the possible values. It's a distribution of over x. It should sum to 1. Right? But if I make this assumption that these variables, attributes are independent of each other, then we learned a joint probability theorem in the basic statistics class. What is the probability of joint probability of A and B if A and B are independent?
P of A into P of B.
Just multiply the individual probabilities, right? Okay. Right.
Can we have this assumption for highly correlated variables or features?
You can always make assumptions, right? They may not be correct, but you can always make them. Yeah, it's not a good idea when there is high correlation, and we will see like where naive Bayes will fail. Right? So now, instead of 2 to the power n minus 1, here we just have 2 variables. But if we had n variables, how many probabilities we need to compute?
n square.
N square, why?
The n times you multiply with other n variables. For example,
N times other multiple variables. Just n.
n power n.
N factorial.
No, n power n. I'm going to name n times again n. Maybe n times n, sir. N power n.
N times number of classes. Okay?
Maybe like n variables multiplied by n variables. It's like n power n, I guess.
Okay? Yes?
Just n, because they're independent. So
Just n.
apply them together.
Just n. Right? Because each of them are a binary random variable. So for A, you have 1. For B, you have a 1. If you have n, then you have n. So we have drastically gone down from 2 to the power n to n. It's a dumb model, but it's a very efficient model. Because you don't need to consider all the possible combinations for computing probabilities. All you need to look at individual variables and just compute their probabilities. You don't care. When you look at B, you don't care about A or C. Because they are binary, we have assumed right now, so it's just one number. Because the other one is 1 minus that. So you just compute one number for each of them. Right? Okay. So now tell me, if y is a binary random variable, then how many do you need here and here to learn?
How many y's? Oh, binary, so n plus.
How many probabilities?
Oh, n plus 1,
N plus 1?
because then you can 1 minus for the other binary value of y.
So here is the thing, you are looking at P of x given y, right? We have considered this case, that x could be this many combinations and x could be this many combinations. But how many y could be? 2. So multiply by 2. Right? So that's what you see here. If you don't make the independence assumption, you need this many probabilities to be computed. But if you make the assumptions, you just need 2n. Questions? Yes.
So you do probability of x, whatever, so x of I, given y, and then you also do the other ones, that's why you do 2n, so you do not y. Do they ever do just 1 minus the first probability, or do they always recalculate for the second one? That makes sense. Or do they do that? Do they do the 1 minus some of the rest of the possibility trick for the p of x given y?
So is your question okay, probability of x 1 given y equals to 1 versus probability of x1 given y equals to 0. Do you do any connection between them?
That's exactly what
You cannot.
Okay.
Unless there is some explicit definition.
So, in the case that y is, it can't possibly be this simple, but in the case that y is not Boolean, does that just increase the, instead of 2, it would just be 3 or 4?
Yeah.
That's really it?
Yeah. Yeah. That's it. But the point is, y is not going to be exponentially large because these are real labels. As humans, we don't want to deal with thousands of labels. That's the good part of it. Okay? All right. So,
It's the same for the x as well. Like if it's not binary, it will be.
it's the same for x as well, right? I mean, you need to consider all possible discrete values if you have. You just extend the possibilities.
Like if we have 4 for each of them, it will be 3 multiplied by n.
So, if it has A has 4 possible values. You need 3 values for this one. So you do 3 for B, do 3 for this. So that becomes 3 to the power n. Right?
So why, if it's 3 to the n, why we got n when we have binary? If you're multiplying it.
Oh, I'm saying about this case. Yeah, if you do a independence assumption, right? So then what happens?
Should be 3 multiplied by n?
Yeah. So think about this. You just have 4 cases. So you just need 3 values for one variable. Now you have n different possibilities. So that becomes 3n. Right? Yeah. Yes.
So the algorithm just assembles this database of probabilities, and then it looks at each data point, calculates the probability, and picks the highest one and says that's what it is?
Yeah. Yeah. And that's why it's not very efficient in real time as well. Okay. So what we have done is we have replaced, you remember this one was our argmax. We want to find out the maximum posterior. This is the prior, but the likelihood part has been replaced with a multiplication over each attribute. So that's the difference here. We have replaced this with a multiplication with the independence assumption. Right? And then we are looking at each attribute individually. Xi instead of the whole x. X new is the set of values for entire x, and xi is just one attribute. So think about the like decision tree problem. This is just weather or humidity or something, not a combination of weather, humidity, and everything. Okay? So all you do, how do you then do the training and testing? The question that you had is basically during the training, you basically compute based on the training data set, what you have, you compute the priors and the likelihoods. And then once you get a new data set in the testing phase, you just multiply those likelihoods and the prior to figure out whatever yk is maximum. And that becomes your label. All right? Okay, what can be a problem with this kind of approaches? Okay, let's first talk about how do we estimate this. Let's say we want to estimate the first one, the prior probability that y. So we need to, again, estimate 2 probabilities, right? One is probability of x given y and the probability of y. So let's talk about this one. Probability of y is equal to yk. So that means probability of the play tennis variable equals to yes and no. How can we, so essentially in the classic example, probability of play tennis equals to yes, and probability of play tennis equals no. We need to estimate these 2 things, right? These are our 2 labels. Now let's say I gave you the toy data set that we have shown in the decision tree example. How do we figure out these probabilities? How do we compute them, estimate them?
Number of yes over total number.
Okay? So in the original data set, how many yes were there?
9.
9,
14.
right? 9 positive. So we can estimate from the data set that this is 9 by 14. What about this?
5.
5
14.
by 14, or 1 minus
9 by
9 by 14, right? That is 5 divided by 14. So from the training data set, we can easily compute this, right? Can we compute this one as well from the training data set? How about that?
So every attribute has equal weight, I guess, right?
So you need to figure out what is probability of whether equal, let's say, sunny, and let's assume just two attributes. Humidity is equals to high given play tennis is equal to yes. How can we estimate this from the data set? Yes.
That's an and you have between sunny and high?
Yes. Because each condition in the particular sample is true, right? That's an and condition. All of them are true. We are given that table, 14 example table. How do we compute this?
You look at all the times that play tennis is yes and count how many those are correct for.
So first of all, count how many, for how many play tennis is equals to yes. Yes. Then on the top, how many times all three are true, right? How many times whether, it's basically sunny, count of sunny, high, and yes, right? Okay, so we can compute the prior, we can compute for all combinations. You can see is how many combinations we have to actually compute, but the point is you can compute if there is enough data. But what is a problem with this kind of counting? Yes?
If you don't have in your upcoming test set that specific one, so it doesn't have all the data.
Right. First of all, if you haven't seen anything like this in the training data, in the testing data, that count will be 0. And in many, many cases, you will see a lot of zeros. Because if your training data is small and the number of combinations you can have, we have already seen just with 100 attributes, binary variables, it will be 2 to the power 100. Right? And we cannot have all of them. So that's why we made this naive Bayes assumption that instead of this, we'll do something else. We will compute individually for count of sunny and with yes, and then we will do another count of humidity high with yes divided by yes. We have two different probabilities and we will multiply. Right? The independence assumption, the naive Bayes algorithm. Chances are you will see more example of this than example where you have sunny, high, and yes. This is less likely to happen than this. And here we are talking about just one attribute, but if you can now extend it to 100 attributes, and that will become very sparse. You will not probably see examples for many of them. And even for some of them, you will just see 1 or 2 cases. Those statistics will not be significant, the probabilities. Okay?
Can you assign weights
Weights for what?
for different attributes in this?
You can always assign weights, but that depends on, so that basically means you have a different model than the Bayesian theorem, where you are you basically are estimating probabilities, but then your decision is a modified version where you have some particular weights. But that's the follow-up stage. But still, here you need this. First, you need these probabilities anyway. Then you can assign weights. So we have reduced the problem space from 2 to the power 100 to 2n, 2 times 100, let's say. But if we just do at individual example levels, have we solved the problem?
No,
Why not?
you have to combine them.
Yes, but think about attributes with so many different discrete values. Think about a particular value for a particular variable. If that becomes 0, because you haven't seen anything like that in the training example, what happens to the entire probability? So that's a multiplication by 0 problem, right? That's a big problem. For example, you have 100 attributes here, right? Probability of x1 given y, x2 given y. You are going like this, x100 given y, right? You have meticulously computed this, and you are computing, multiplying, all the hard work is done, and this guy is 0. What happens? Everything is 0. That's another problem, right? So we need to handle multiplication by 0 problem, as well as the assumption itself may not be true. The data may not be, maybe highly correlated attributes are there, and the assumption we are making is not true. So it depends on the application we are doing, whether that is a right choice or not. But turns out, for a lot of use cases, naive Bayes is pretty good. Text classification is one classical example.
So to handle that 0, do you just neglect it? You just forget it in this approach?
That depends on how you want to handle it, and we'll see how we can handle it. There are ways. So that's basically called smoothing, right? You basically assign some prior probabilities that it can never be 0. It has to be some minimum values. You have to force non-zero values. Okay? Yeah, we have seen this example, and we can compute numbers like this, but even then they can become 0. And the issues are, there are cases where naive Bayes assumption will be violated, and the use cases will not be properly served. And then we need to handle these 0 probability issues, right? If one term is 0, we will be essentially computing 0, because multiplication by 0 is 0. So we kind of do some tricks. Instead of this count divided by this, one simple idea is to just say this count is always plus by 1. Dumb, but works. It's called Laplace smoothing. But then just adding 1 here is not enough. You need to add something here as well. Why?
The ratio would be incorrect for non-zero numbers.
Because you're increasing the probability mass here, and they have to sum to 1. So you have to account for that here as well. Right? If, for example, you see if your distinct number of values are k, right? And I determines the strength of the smoothing. So forget the smoothing part. Just think about the different kind of values. So you are adding 1 to k different values. So to make sure that they sum to 1, you need to the denominator has to be normalized with k. Because for k different cases, you are adding 1 to the mass. It will ensure that if you sum all of them, because each one of them has got k in the denominator, and you are adding 1 for k cases, if you add all those probabilities, you will have a k on the top as well, and you will get 1. So it's like basically saying, even if I don't see any example of this kind, there is at least one count in my training data set. So my training data set by default has one count for all possible cases, which is a reasonable assumption to make. You are just shifting the problem. Okay? So now let's look at a practical example. So the bag of words. How many of you have heard this term, bag of words? Okay, so this is what a bag of word representation looks like. So this is the document, right? And on the right, this representation, what is this? What do you see here?
Count of how many times the word shows up.
Frequency count of words, right? Individual words. And it's like if you have a bag, you put all the words there in the bag in random order. You don't care about the order. You just care about how many, you have some balls, and then you have blue and red and green with different colors. You can just say, okay, I have got 5 green balls in my bag, and that's it. You don't really know which order, and the order is lost. It's just in a bag. So it's like this document, if you do a bag of word representation, that becomes something like this, and this order is also, doesn't matter. You could have it in any different order. And then, now, can anybody tell me like how this bag of word representation connects to naive Bayes theorem? Why bag of word representation is something that connects to naive Bayes? Okay, what is the assumption in naive Bayes?
That all of them are independent.
Independent. Okay, in terms of a document, what does that mean?
All the words are unshot, or they're put all into a bag. So we're then, oh, this is the same thing as the bag analogy when you're doing Bayes' theorem with the bag.
Exactly. When you are saying x1, x2, x3, they have no connection between them. What is x1, x2, x3 in terms of a document? Think about this. Think about this. You have a document, right? You have a document that has word 1, word 2, word 3, and so on. You just keep writing. It's a ChatGPT printing, right? WN. Now you could essentially say that each position is a feature. You could represent the document in that way, right? For example, you could say W1 is the X1. This is X2. This is X3. So this document representation, this is the X. The document is represented by this, each position. But when we say, let's say this is X4, right? When we say what is the probability that you will say W4 in the 4th position, in reality, that basically means what is the probability that you will see W4 given that you have already seen W1, W2, W3. right? Because that's how we write text. Let's say I say I go to, what goes here?
College.
College?
Maybe it can be anything.
Can it be rice? Can it be Coke? No. So this probability is highly dependent on what we see here. But what naive Bayes is basically saying, what it is saying?
Independent.
It doesn't matter. It doesn't matter. Doesn't matter. Yes?
So it's just equally distributing the words. If we were going through this document, it would say like, it has this % chance that the first word is, aardvark or whatever, and you would end up with a document that is just equal distribution probability of the word showing up.
It's not going to be equal. It depends on how many words you have in your document and what is the characteristic of your document, right? In general, stop words will have a higher count. A, and, the, and then there will be some topic words. But it turns out, still just a simple frequency count with this naive Bayes classification works for classifying documents.
Into what categories?
Your topics.
Topic choice, okay.
What are the topics of this document? Sorry, what?
The 4W4 order is related to the location.
Is the location of the document. Yes. So it's important to figure out this X4. Actually, your question is, yes, I see what you mean. So the fourth position here, this 4 is important here. So that is the I equals to 4. But this W will come from a vocabulary, right? And this position I will be the length of the document. The number of words you have in a document, that is your index. So these two are different things, and we will see the two different representations for this as well. But the whole point is, in naive Bayes, you are basically saying, if rather than saying what is the probability of entire this sequence, and what is, if I, again coming back, if I don't make a naive Bayes assumption, what is a problem of computing probability of document, a particular document given, let's say it's about sports. And I want to find out what is the probability of this entire document. If I don't do naive Bayes assumption, what is the problem with this?
You're not going to have that exact combination.
Because this document is unique, let's say. Because you are not likely to see this same document, then there is no point in writing, right? I mean, that is plagiarism. So you have never seen this document before. So if you don't make an assumption, you have never seen this sequence, so you cannot even estimate a probability of this. So that's why, instead of this, we are making the independence assumption, and we are saying, what is the probability that we have seen baseball 3 times, and we have seen Auburn 2 times, and blah, blah, blah. What is the probability of seeing these words this many times, given that it is about sports? That is still, that's a little better than the sequence, but still seeing all of them together is still sparse. What is the probability that you will see, probability that baseball equals to 3 given sports? And what is the probability that you will see Auburn equals to 2 given sports? This is more likely to be non-zero than everything like together happening in your training corpus. So the whole point in naive Bayes is to be naive keep being naive as long as you don't have sufficient counts to estimate reliable probabilities. So the Bayes theorem, which is cool, doesn't actually solve our real life problems a lot of times because we cannot estimate those probabilities. And being naive in terms of making dumb assumptions that helps us compute these individual probabilities in a more robust way. And then just multiply them with that trick that we force these probabilities to be non-zero. We don't allow them to be zero. That is the naive Bayes algorithm. Questions? Yes.
So with baseball equals 3, how do you select that tree there? And like how, this is more like probability question. Like if you choose 1, how it will impact the probability?
So now it becomes, instead of a label, it's a continuous variable, right? It's a count. So it's basically in your input document that you want to classify. You now have 3 times the word baseball appearing. And you want to find out how likely baseball is to appear 3 times in a document that is about sports. So you have in your training data set, you have many sports documents, right? And let's say you can count the number of times baseball appeared in those sports documents. And based on that, you could estimate a distribution. And then you could assign a probability to the number 3, how likely that is, based on your training data. Okay? Just to simplify, even if it is not continuous like count, let's say it's binary, 1 or 0, whether baseball appears in a sports document or not, then in your training corpus, you could look at all the sports articles and you could count in how many of them baseball word appears or not. Right? And we'll see the continuous case, how to handle them. Okay. So text classification, we could do many interesting things with this kind of naive Bayes classifiers. We could classify emails, like whether it's a spam or not. Right? If I give you a training data set with different emails and your labels, yes, no, for spam, then you could create over the entire vocabulary of words, what is the distribution of individual words when it is a spam versus what is the distribution of individual words when it's not spam. And then you could compute, given a new email, you could look at these words and look at these numbers, how many times they appear, and based on that, apply naive Bayes to classify whether it's a spam or not. You could do the same thing for finding out the topic of the document. You could find out whether web pages in a university belongs to a student, a professor, or a project or something, right? As long as it's and what is the feature? The feature is your text, this text. And here we just saw one way to do the featuring. That is, each position is one feature, but we can have alternative as well. What is a problem with the position as feature? If I have positions, each position, word position is one feature like X. What is a problem in machine learning? Yes?
Documents different sizes?
Yes, each document has different size. Then you need a different size representation for each document. That's a problem. You want a uniform representation to do machine learning, right? How do we solve this? So the document, instead of representing them in terms of the word positions in the document, what else we could do? Yes?
Bag of words.
Bag of words. So you basically, instead of saying the positions, you just say each document is essentially a vector over all the words in the vocabulary. All the words. Now you just say, okay, how many words, how many times I see W2 in this document? Let's say 2 times. W1 I don't see. W3 I see it once, and so on. What is the good thing about this? Now you have a single representation that can represent any document. because your vocabulary set is fixed. Let's say in English word, how many words we will have? Let's say 30,000. That's your feature size. So whenever you are dealing with text document that is in English, probably you are dealing with a feature space of 30,000 and maybe more, if you use individual words as features. And that's a fixed size representation. What is the problem with this kind of representation? Yes?
You may miss specific words if it's more like niche subjects.
Yeah, frame it in terms of numbers.
You're going to end up with a probability of 0 if it's 30,000, I'm looking for...
Most of the words will be 0 for a document,
Yeah.
right? Most of the counts for a particular document will be 0. So it's basically you are dealing with sparse vectors. So whatever vector arithmetic you are going to do, that will have this issue of sparse vectors. And then there are ways, efficient algorithms to handle sparse vectors, right? And people resort to that. So here is a document, right? So it's just showing the same numbers that we talked about. Let's say one article has got 1,000 words, that's the length. Now, if you have a vocabulary of 10,000, so the point is your vocabulary size, let's say it's not 30,000, it's 10,000. 10,000 vocabulary size, V. And you have a document that is 1,000 words long, length. Right? So X, if we represent by the position, right? How many probabilities we need to compute? Even after we apply the naive Bayes assumption. Think about this. You have a 1,000 length document. So each position, 1, 2, 3, 4, 5. For each position,
Can have 30,000?
till 1,000, and this is the vocabulary size. So first position, how many values is possible?
10,000.
10,000. How many?
9,909.
10,000.
Why not? Why not everyone? Because words can be repeated, right? This is a document, right? So the same word can appear twice. So each place 10,000, 100,000 times, right? That's the number you are looking at. That's still big. And that's why having positions as a representation is not a good idea anyway. Right?
Can you separate documents into like opening, or like first 10%, second 10% of the document? Is that a decent way to do it instead of just a general bag saying the first 10% of a document?
You can always do paragraph level segmentation. Is that what you are talking about?
Yeah, that or...
If you even do paragraph level, that is still a document that can have, a paragraph is still a document that can have any word from the vocabulary, and a common representation will have to have all the words in the vocabulary. That doesn't solve the real problem. But we'll see from 30,000 to down to like few hundreds how we come up with that. Although we'll not teach it in this course. That's part of the NLP course I teach. It's the deep semantic features, the word embeddings, the deep learning, all those things, right? Transformers, BERT. Yes?
So I think or at least I saw this when we were doing Markov chains in earlier classes. You could split it into like 2 or 3 word runs to maybe get more fidelity on what you're trying to do.
Yes. So what you mention is basically the n-gram model. Instead of looking at individual words, at least we could consider pairs or triplets. And this is just, n is 1 here, which is called a unigram language model. Right now, the bag of word is essentially the unigram language model. And we will continue this in our next lecture. We are not done yet with Naive, but we will release the assignment today so that you can start working. But we will wrap it up, this topic, in the next class, and we will move forward to the other topic. Thank you very much. See you on Thursday.
Thank you.